All right, look at the solutions for our review for our third and final regular test of the semester. So we have a couple things here. It says sine is equal to 1/5 in quadrant 1. So anytime you see something like this, probably a good idea to go ahead and set up your triangle. So we have a triangle in quadrant 1 with angle theta. And then of course it's sine, so that's opposite over hypotenuse. I think it would be a good idea to obviously find the other side. So I'll just use the Pythagorean theorem to find my other side. So that is going to be 5 squared equals the side squared plus 1 squared. 25 minus 1, which is 24. So taking the square root, my other side is the square root of 24, or that is 2 root 6 if I simplify it. Okay? So that is my triangle for theta. Now this problem actually has a second triangle. It says there's also cosine of beta. So that's a new angle in quadrant 4 this time, so down here. And when you're not in quadrant 1, remember you have negative and positive sides. So cosine is the adjacent over the hypotenuse. So square root of 3 over 4. And again, I'll do the Pythagorean theorem. 4 squared equals square root of 3 squared plus y squared, because it's kind of the y distance. And I know this will be negative because it's going down. So 16 equals 3 plus y squared. Subtract 3, I get y squared is 13. Take the square root of both sides, so I get square root of 13, which is negative based on its position. So this is triangle beta. So now if I'm looking for things that have a theta, I'll use the first triangle. If I'm looking for things with a beta, I'll use the second. So for example, cosecant of theta is the flip of sine, so that's just 5. That's pretty simple based on my given sine ratio, or it's hypotenuse over opposite, same thing. The cosine of theta is 2 square root of 6, which is the adjacent over the hypotenuse, which is 5. So 2 root 6 over 5. Now number 3 says find the sine of beta. So that's going to hop over to my red triangle. And the sine of beta is opposite over hypotenuse on the red triangle. So those are just basic trig function values. And the reason we set those up is we'll definitely need them when we do some of our identity problems here at the bottom. So we have cosine of theta minus beta, cosine of 2 theta, and sine of 2 theta. Now remember, for all these, we're going to have to use our identities that are on our sheet. So we'll do that. So if I look at my identity sheet for cosine of theta minus beta, you can kind of think of this as angle A, this is angle B. I'll get cosine of theta, cosine of beta, plus sine of the first angle, which is theta, sine of the second angle, which is beta. Now all of these values, they're just things on the triangles of theta and beta. So cosine of theta, I found up here in number 2, so that's 2 root 6 over 5. The cosine of beta, I go to the other triangle, and it's actually given to me as well. That's square root of 3 over 4. Sine of theta was given to me, or I can use the black triangle up there, so that's 1 over 5. And the sine of beta, which is going to be the red triangle, I found in number 3, so that's negative root 13 over 4. So I just find the identity from my sheet, and then I'll simplify. So if I clean this up a little bit, I get 2 square root of 18 over 20 plus negative radical 13 over 20. Now I can simplify radical 18. It's 9 and 2, so the square root of 9 is 3. So that's 2 times 3, which is 6, square root of 2 over 20, minus square root of 13 over 20. So this identity is a little trickier because you actually have to use 2 triangles. You have to use the theta and the beta. Now 5 and 6 are not quite as difficult identities because they literally only have one angle. They only have theta. So when I look at the identities, they're only going to use one angle. So cosine 2 theta, I'm going to look on my identity sheet for something that has cosine 2 theta. That's going to be a double angle identity. So I would look on there for an identity for cosine 2 theta. And ironically, there are lots of identities for that. One of them is 1 minus 2 sine squared theta. I would encourage you to look on your identity sheet where I'm getting that about halfway down under the double angles. You could also use cosine squared minus sine squared, or 2 cosine squared minus 1. So my value is going to be 2 minus 1/5 squared, because remember, up here we said sine of theta is 1/5. So I'm just replacing sine with 1/5. Now I'm just going to do some basic math. 1/5 times 1/5 is 1/25. 1 minus 2/25, because 2 over 1 multiplied. So that's going to be 23/25. Now these double identical angles or identities are more likely the ones you'll probably see on your test versus the sum and difference ones we saw in the first one. So just kind of a piece of advice. Sine of 2 theta is 2 sine cosine. Again, an identity from our sheet. This is really the only one we have. So sine, we said again, sine is 1/5. That was given us 2 in the problem. And cosine, we found in number 2 to be 2 root 6 over 5. So I'll just multiply across 4 square root of 6 over 25. So just using our identities from the sheet and our triangles that we set up in the first part. All right, let's go ahead and look at some other ways we can use these identities, namely using exact values. So these are the ones where you're finding things that aren't on the unit circle, using things that are on the unit circle. So you can use the sum or difference, or you can use the half angle. Some of them you really don't have a choice, some of them you do. So for example, I actually could use half angle or sum angle formula for the first one and the second one. The third one I kind of have to use half angle. So I think the easiest one for this one is I would probably find 2 angles that subtract to 75. So maybe 30 minus, no, 30 won't work. Let's do 60 minus 135. That works. So that's my angle A and my angle B. So we know from our identity chart, sine of A plus B, sine of A minus B, because we're subtracting angles. Sine of A, cosine of B, minus sine of B, cosine of A. So once you have that, we know what our A and B are, so we're just finding what's the sine of 60 times the cosine of 135 minus the sine of 135 times the cosine of 60. Now all these values should be on the unit circle, so you could just go to your unit circle and find all these values and simplify it out. So if I was doing sine of 60 is the y value. So that's going to be square root of 3 over 2. Cosine of 135 is negative square root of 2 over 2. Sine of 135 is positive square root of 2 over 2. And cosine of 60 is 1/2. So when we simplify this out, we get negative square root of 6 over 4 minus square root of 2 over 4, which is negative square root of 6 minus square root of 2 all over 4. And we've seen this pattern before. We've seen this quite a few times where we have these kind of numbers in this iteration. All right, now for tan of 15. You could do 2 things that add or 2 things that subtract to 15, but that's going to be a much harder way. If I was going to do this, I would do the half angle formula, which says that if I have tangent of an angle divided by 2, that's 1 minus cosine theta over sine theta. So you can look at this on your identity sheets under the half angle identities, almost toward the bottom. So we have to think about what angle would I cut in half to get 15, and it would be 30. So the tangent of 30 divided by 2, so in this formula, I would put 30 in for these 2 values. So I would end up with 1 minus cosine of 30 over sine of 30. And then I could just get those values from my unit circle. So this is 1 minus square root of 3 over 2, and this is 1/2 on the bottom. And you can look at your unit circle for that. And this one's really, really simplified. It's easy to simplify. Multiply everything by 2. So I get 2 minus the square root of 3 over 1. So if you remember how hard that was when we actually did it with the sum and difference, with the conjugation and all that, this is a whole heck of a lot easier. Now cosine of 22.5, you don't really have a choice because, you know, it's 22.5. There's no angles that are going to add or subtract to 22.5 on the unit circle. But I can cut an angle in half using the whole cosine half angle identity. Cosine theta over 2 is 1 plus cosine theta over 2. So kind of the same thing we did on the tangent. What angle cut in half is 22.5? It's 45. So this is my theta angle that I use in this. So 22.5 is positive, so that's 1 plus cosine 45 over 2. So remember, when you're plugging in a half angle identity, you have to think about what angle are you cutting in half. So that's square root of 1 plus root 2 over 2, all over 2. I'll go ahead and multiply everything by 2. So I'll get the square root of 2 plus the square root of 2 on top. And the bottom is just the square root of 4, and the square root of 4 is just 2 outside the root. So, kind of a wide variety of different problems here. So I would expect to see some of these, obviously, on your test. All right, let's look at a couple more problems. So these next ones, we have simplifying and proving identities like we did at the beginning of Chapter 7. So simplify sine squared plus cosine squared equals 1, or plus cotangent squared. But I do know this is a pretty fundamental identity that sine squared plus cosine squared is 1 plus cotangent squared x. So this is just on my identity sheet. This is a Pythagorean identity. But ironically, when I put that to 1, 1 plus cotangent squared is also a fundamental identity. So 1 plus cotangent squared is just cosecant squared x. So pretty simple one, just using our Pythagorean identities to simplify to a single expression. All right, for this next one, there's not a ton we can do with this one. Cosine 2x, so this is a double angle formula here. So I know cosine 2x is cosine squared x minus sine squared x, all over sine squared x. So the best I could do is I could break this apart. I could do cosine squared x over sine squared x minus sine squared x over sine squared x. So that's cotangent squared x, because cosine over sine is cotangent, minus 1. Now that doesn't really, cotangent squared plus 1 is an identity, but minus 1 really isn't anything. So that's pretty much the furthest we can take this one. So not the best one because it doesn't get to a single expression, but it definitely simplifies a little bit. Now 11, we're dealing with an identity where we know the answer. We know the answer is cotangent squared y. So I just got to try to figure out why does this nightmare on the left turn into cotangent squared y. So if you remember how we approached these proofs, we said if there's anything that's not sine or cosine, I'm going to probably turn it to sine or cosine. So I have sine times 1 over sine plus cosine squared 1 over sine squared, because we have cosecant, which is 1 over sine. And on the bottom I have 1 over cosine squared. Okay? So on the top I can obviously cancel out my sines. So I'll be left with 1. And then I have cosine over sine here. Cosine over sine is cotangent squared over 1 over cosine squared y. Now good news, 1 plus cotangent squared is an identity. So if you look at 1 plus cotangent squared on our identity sheet, it is cosecant squared. All right, so now we're getting somewhere. So we've taken the 1 plus cotangent squared, got cosecant. So we're left with 1 over sine squared y, 1 over cosine squared y. So good news, we have the keep, change, flip. So this will simply become 1 over sine squared times cosine squared over 1. So we have cosine over sine, which is just simply cotangent, which is what I wanted it to be. So there you are. So not too terrible of one. Obviously, a lot of steps in this one, but we get to the other side. I would not expect the one on your test to be more than 2 or 3 steps. This one may be a little longer than that, but nothing too terrible. So our last big topic in Chapter 7, we're doing these identities, where you're either trying to factor or just get linear ones by themselves. So 12 looks like a nonlinear equation because we have the square. So typically when I have that, I'm going to try to make it into a kind of descending power thing. So 2 sine squared, because square is the biggest, plus 3 sine x, plus 1 equals 0. So this in class is when we took the substitution variable, said u equals sine x. And so we'd simply get 2u squared plus 3u plus 1 equals 0. So you only do this substitution when it's like a quadratic, a square. Like 13, we will not do it. It'll be much easier because it's one of the unit circle ones. So we'll factor this. So 2u and u, plus 1, not a ton of choices here. So we get 2u plus 1 equals 0, u plus 1 equals 0. So u equals negative 1/2 when I subtract 1 to divide 2, and u equals negative 1. Now the big thing to remember in a quadratic one, you want to make sure that you plug back in whatever you were working with. So sine x equals to negative 1/2. Sine x equals to negative 1. So now I'll just look on my unit circle for these values. So sine is negative 1/2, that's the y value, so that's going to be at 7 pi over 6 and 11 pi over 6. And I encourage you, again, look at your unit circle, make sure you're seeing where I get these. And then sine is negative 1 at 3 pi over 2. You're obviously welcome to use degrees if you'd like, because this case it didn't really say. It said you could use radians or degrees. I chose to do radians. So whenever you see the square, that's going to be a pretty good sign you're going to have to do some kind of factorization. Now 13 is actually a much easier problem because it's just linear. There's no square or anything like that. So I'll just get my trig function by itself. I'll just add square root of 2, and then I'll divide by 2. So sine x equals the square root of 2 over 2. Then I can simply look on my unit circle. Again, sine is the y. Where is y equal to square root of 2 over 2? And that would be at pi over 4, and that would be at 3 pi over 4. So when they're linear like that, there's really nothing to it. So my final equation is tan x equal 1. So tan x equal 1, I'm trying to find where the tangent is 1 on the unit circle. Now remember, tangent on the unit circle is y over x. So I'm trying to figure out where on the unit circle would I divide the y and the x and get 1. Well, if I look at my unit circle, I want it to be the same. So one place where I see y and x are the same is here at pi over 4. And then the cool thing is about tangent, the other solution has to be directly across from it. So if I look at this point down here, negative root 2 over 2, negative root 2 over 2, divide those two negative values, I obviously get positive 1 as well. So straight across pi over 4 on the unit circle is 5 pi over 4, so that would be my other solution. All right, the last problem that we had was these vector problems. These will be the last ones on the test. So if we have two vectors, let's say we have vectors 3, negative 4 is vector A. Now I have it written in the unit vector notation, but we could certainly just change it. Vector B is negative 2, 5. So it says, what is vector A plus B? Well, for A plus B, we simply add the x's and add the y's. So 3 plus negative 2 is 1. Negative 4 plus 5 is 1. So now this is vector A plus B. So question B says, what's the magnitude of this vector? So magnitude is just the square root of the component squared. So that's going to be the square root of 1 plus 1, or the square root of 2. Now just for fun, I am going to draw this vector, which happens to be in quadrant 1, which is really nice. So what that's saying, the magnitude is how long this vector is, so this is square root of 2. All right, C says, what is the direction? So the direction is simply going to be this angle in quadrant 1. Now we know our reference angle is given by the equation inverse tan of y over x, always positive. So we can find our reference angle here by taking what's the inverse tangent of 1 divided by 1. Now if I put this in the calculator, you should get 45. And the good news is, because I'm in quadrant 1, the reference angle is the same. Now, like we did before, if you're in a different quadrant, you might have to do something slightly different. D says, what is vector negative 4a minus 7b? Well, this is just when we multiply vector a by negative 4. And then we multiply vector b by negative 7. So that's going to be, I'm going to multiply negative 4 to this, so that's going to be negative 12 and positive 16. And I'm going to go ahead and distribute the whole negative 7, which will make it a positive. So plus 14 and negative 35. So when I add those vectors, I'll get 2, because I'm adding the x's. And then 16 and negative 35 is negative 19. Now our last problem says, let's find the angle between these two vectors. This is the most recent stuff we did using dot products. So if you recall, we have this formula, the cosine of theta is equal to a dot b over magnitude A, magnitude B. So we remember our vectors up here. So we don't worry about the sum vectors now. We're going to worry about our original vectors, 3, negative 4 for A, and negative 2, 5 for B. So cosine of theta is going to equal a dot b. That's when you multiply the x's and add them to the product of the y's over the magnitude of each vector. So magnitude of A is going to be 3 squared plus negative 4 squared. And B is going to be negative 2 squared plus 5 squared. So that's going to give me cosine theta, that's negative 6 and negative 20, which is negative 26, over, this is 3, that's 9 is 16, which is 25, square root of 25 is 5. And again, you should definitely verify these. 2 squared is 4, plus 25 is 29. So now to finish this up, I simply just take the inverse cosine of negative 26 over 5 radical 29, and that yields me 164.93. So that's the angle between these two vectors. So if I were to graph these two vectors, 3, negative 4, which would be somewhere over here, and then negative 2, 5, which is somewhere up here, this angle, which you can kind of see from my crude picture, is a pretty big angle. We say that angle is about 164.93. So that is our review for test 3. It will end at vectors. So mine has polar on it. Don't worry about that. Yours does not. This is what your test is kind of going to be based on next week. If you have any questions, obviously bring those to class so we can get those answered before we take the test.